Mark Krumholz, an astrophysicist from the Australian National University. Professor Krumholz Professor Krumholz has done significant research on formation of stars and galaxies, and we are pleased to have Sir with us today as he was kind enough to accept our invitation. We'll take questions at the end of the lecture, and let's try to learn something new today, guys.
Thank you very much. Well, thank you for that introduction and for inviting me. I'm guessing that at least some of you know that a former BITS Pilani student is finishing his PhD with me right now. In fact, has just filed his thesis, and we are waiting for the reviewer comments on it, Pia Sharda, and we'll be going on to a postdoc in the Netherlands thereafter. So I'm very pleased to be speaking to you. And I would like to tell you a little something about what sets the masses of stars. All right, now I know that I'm talking to an audience of largely of students and some non-astronomers, so I will try and provide some background on this topic. So I'll start with an introduction of what is the IMF, the thing I'm going to be talking about, and why does it matter, and what do observations tell us about it. I will then talk about theoretical models that we use to try and understand this thing, the IMF, and I will discuss some general considerations and then some models in particular for the origin of the mass scale in the IMF, which sets the characteristic masses of stars, and then I'll summarize. All right, so let's start with part one. What is the IMF? Let me start with that. So the IMF, well, it's not the International Monetary Fund. And the problem with Zoom is I can't tell if anyone is finding any of my jokes funny. So I am just going to assume that you are all finding me completely hilarious and are laughing uproariously at everything I say because the alternative is too depressing to contemplate. So I'm just going to assume you think my jokes are funny. All right, so the IMF. The IMF is the initial mass function. So what's the initial mass function? Well, it's the function that describes the distribution of the masses of stars at birth meaning before there's been any significant changes in stars' masses due to stellar winds, due to them blowing up as supernovae, etc. All right, so it's simply a statistical distribution of when a bunch of stars form, how many one solar mass stars will there be versus two solar mass versus three versus four. What are the relative frequencies of the different masses that stars could have at birth before any of those, say, 20 solar mass stars blow up as supernova? Now, for low mass stars, those that are like the sun or less, the initial mass is nearly identical to the present day mass, at least for a long time. The sun has lost a little bit of its mass over its lifetime, but we're talking about a few percent, in fact, less than a few percent. So for stars like the sun, the initial mass and the present day mass are basically the same. On the other hand, if we go to massive stars, things that are, say, 10 solar masses or more, then you have to measure their masses when they have ages of only 1 or 2 million years because they will blow up before much longer than that. All right, so that's what we mean by the initial mass function in practice. Now, why does it matter? Why is it interesting to measure the IMF? Well, I mean, partly it's interesting just because it's interesting, but it's also interesting for lots of other reasons. And the fundamental reason is that stars are the nuclear reactors that serve as the engines of the universe. Most of the light in the universe is starlight. Stars and their supernova explosions are the dominant source of energy that regulates the formation of galaxies. Stars produce almost all of the chemical elements heavier than hydrogen and helium. And of course, the warm zones around stars likely determine where life can evolve. So stars matter a lot for all of these things, and they matter because they're nuclear reactors. But stars of different masses are nuclear reactors of very different power and efficiency. So to take the extreme examples, a 100 solar mass star will convert about 0.5% of its initial mass into light in about 3 million years. The process of fusing hydrogen into helium releases some of the mass as light, and that's what makes the star light up. And if you just work out the budgets, a 100 solar mass star will turn about 0.5% of the mass it's born with into light over a time span of about 3 million years. On the other hand, a 1 solar mass star like the sun will convert about 0.1% of its initial mass into light, and it will take 10 billion years, 10 gigayears to do so. So a 100 solar mass star is a far more efficient and powerful reactor than a 1 solar mass star. So it matters how many 100 solar mass stars we have versus how many 1 solar mass stars for all of these purposes. So how do we measure the IMF? Well, there are lots of ways. Near the sun, the most basic way is to make something like a color magnitude diagram. I'm showing one here, and this particular one comes from Salima in 2019. So the way to read this plot is that you find a bunch of stars near the sun, and you can only do this with stars whose distances you know, because you need to know their absolute brightness. You need to know how bright they are, and in order to know how bright they are, you need to know how far away they are. Fortunately, the Gaia satellite has given us lots of stars where we've measured distances. So what I have on the y-axis here is the absolute magnitude of the star. Now, for those of you who are not astronomers, who have not encountered this horror yet, I am now going to apologize on behalf of my field. Astronomers insist on using this thing called the magnitude system. And the insane thing about the magnitude system is that smaller numbers are brighter. It's a backwards scale. We're stuck with it because of ancient Greeks. I'm sorry. Up is brighter on this plot. So you go up, you're brighter, even though the numbers are getting smaller. All right, now the x-axis is the color. It's the difference between magnitudes in two bands, in this case, blue and red. All right, so as you go to the right, you're getting red. And each of these dots on this plot, you can see, is a star, all right, where we measure the color and magnitude. Now, the position along this sequence, you can see that all of these stars follow along a fairly narrow band, which is called the main sequence. The position along this sequence is determined by the mass of the star. And you can see in this plot that it's been broken up into a bunch of bands, and these bands correspond to different mass ranges. So you can see, well, all right, I have stars from 0.235 to 0.28 solar masses, 0.19 to 0.235, etc. So you have models that convert position in the color magnitude diagram to mass, and then you just count the dots in each band. And that gives you a measurement of the IMF. Now, that only works for stars that aren't too massive. And the reason is, this isn't actually a measurement of the IMF, it's a measurement of the present day mass distribution. We said for low mass stars, those are nearly identical because those stars just don't evolve over the age of the universe. But for high mass stars, it's not. All right, I should say, so here are some just different IMFs based on counting the stars in these bins, and you can see in these plots that there's this sort of distinct peak at around a few tenths of a solar mass. All right, so that's for low mass stars. If you want to go to higher mass stars, you have a problem, which is that you can't assume the present day mass is the same as the initial mass. In the extreme, if you're talking about something that's 10 solar masses or more, the present day mass may be 0 because it blew up as a supernova. It's not there anymore. You also, it turns out, have a problem with with very low mass stars or brown dwarfs. And the reason is, it's very hard to count them because they're so dim. They're just not bright enough that you can find large numbers of them, so you don't know how many there are. So the solution to both of these problems is to measure the IMF not for stars around the sun, but to measure the IMF in young star clusters, like the Orion Nebula cluster, which I'm showing here in this picture. So this is a cluster of stars that was born only a couple million years ago. Now this has big advantages. All the massive stars are still there. You can see those very bright stars in the center of the picture. Those are the most massive stars in Orion, and they're there, you can count them. Brown dwarfs, it turns out, are also much easier to find when they're young because they're still hot from having just formed, and that makes them brighter than they will be 5 billion years later. So you can find both the high mass and the low mass stars in the young cluster. And there are challenges too. The statistics are much worse. That diagram I showed you of star counts near the sun had 1 million stars in it. You're not going to get 1 million stars in a single cluster. You also have problems with dust extinction. You can see that this region is very dusty, and so you have to try and adjust your measurements of luminosity for dust absorbing some of the light on its way to you. And for young stars, it's harder to determine the mass from the light because they haven't reached equilibrium yet. Nonetheless, despite these caveats, you can in fact measure the IMF in young clusters. And if you do this, what you find is that the IMF in young clusters is actually pretty similar to that you measure for just stars in the solar neighborhood, at least where they overlap. And it's nearly the same for every cluster you look at. So let's focus on the left panel. Those are the young populations. The right panel is older populations where some of the massive stars have disappeared due to evolution. But if we just focus on the left panel, what you can see, all right, so the dotted line there is just a fit to the mass distribution in the solar neighborhood that you see for not so massive stars. And you can see that it's a reasonable description of all of these clusters. I mean, there are errors, there are uncertainties, but qualitatively, all of these show a sort of broad plateau, which has a peak at around a few tenths of the mass of the sun. All right, at higher masses, it turns out you have this sort of power law fall off, but there's this peak at sort of, 0.2 solar. Now, this is at least a little bit surprising. And the reason is that the clusters I'm showing you here span a huge range of properties. They span a factor of 100,000 in mass and density and metal content, and yet we're getting roughly the same IMF from all of them. All right, so just to put in perspective, like the range of things I'm showing you. One of the clusters I just showed you is IC348. It's about 300 stars. Here's a picture of it. I've helpfully added a scale bar there to show you what a parsec is, about 3 light years. All right, so now let me put this next to, on the same scale as one of the other clusters I showed you. Here is the Orion Nebula cluster. Each of those dots and X's you can see in that picture is an individual star. Orion's got about 3,000 stars in it, and you can see how much bigger it is. But let me add a third cluster of this, and here's the cluster R136, which contains about 1 million stars. And again, I put them all to scale, so you can see how tiny IC348 is compared to R136. You almost can't see it. Nonetheless, all of these regions, which vary hugely in properties, all show this same sort of characteristic mass for their stars. So we have this fundamental observational fact. The universe seems to like to make stars at a particular mass, which is about 20% the mass of the sun. The sun's a little more massive than average, but it's still sort of on the edge of that plateau. Why? Right? This is a deep physics question. The universe likes to set the masses of stars at a particular value. Where does that come from? This is one of the oldest problems in theoretical astrophysics. And just to illustrate how old, I will reprint here some letters. So Arthur Eddington, who I'm sure most of you have heard of, one of the greatest astronomers of the early 20th century, gave a lecture called Diffuse Matter in Interstellar Space. That was the Beckerian lecture to the Royal Society. And he wanted to talk about the properties of the gas between the stars. And one of his questions that he answered is, by this time they had the idea that stars form out of the interstellar medium. What sets the masses of the stars? All right, so he gave a lecture in which he talked about that question. Now, I put this up here partly to show that this is an old question, but partly for the humor value, because this lecture from Eddington drew a response. All right, so I reprint part of it here. And just to remind you, this is all printed in an open journal. These aren't private letters. All right, so he comments, and I'll ask you to take a moment to read. So much work has been done on isothermal equilibrium that it is difficult to understand how Professor Eddington can harbor the illusion that he is doing pioneer work in unexplored territory. Yet his complete absence of reference to other theoretical workers suggests that such is actually the case. So this is a "you didn't cite me" letter. It's a complaint about not being cited from genes, as in the Rayleigh-Jeans distribution and the genes instability. And in fact, the thing he's complaining about Eddington not citing is what we now call the genes instability. this letter draws a response from Eddington in the next issue, and says, I had long admired this ingenious paper. This is a paper about the gene's instability. But having come to the conclusion that the masses of stars are determined by radiation pressure independently of the primitive density, I ceased to accept it. So they're arguing about what sets the masses of stars here in 1926. Jeans responds, may conclude by assuring Professor Eddington, etc. And I'll let you read this. And here's the thing. I love this in part because it shows it's an old problem, and in part because it shows that, you know, these gentlemen astronomers are being very, very polite and proper with one another, and they clearly loathe one another, right? The tone of this letter is, you know, if the learned gentleman would only remove his head from his own hindquarters, he would see, etc. The best part of this, I think, is the fact that both of these guys were working at Cambridge at the time. They weren't in the same department. Jeans was in the Department of Applied Math and Theoretical Physics, and Eddington was out at the observatory. But their offices were literally about 1.5 kilometers apart. Nonetheless, they felt the need to exchange these letters. Just goes to show, great old men of astronomy can be dickheads too. We will move on. Now, I've told you about observations and this old problem about why stars are 20% of the mass of the sun. But there's a wrinkle, which is the IMF seems to be pretty universal, but it's not completely universal. And this is a relatively new development. So the way we were just talking about measuring the IMF is by counting stars. Right? Fundamentally, it's an exercise in counting. You find some population of stars, you figure out the masses of each of those stars somehow, and you just put them in a histogram, and that's the IMF. Now, you can only do that in the most nearby galaxies. You can do it in the Milky Way, you can do it in the Magellanic Clouds, you can do it to some extent in Andromeda, but it starts to get dicey. And if you go beyond the most nearby galaxies, you can't do it anymore, and that's just because you don't have the resolution to separate individual stars. If I look at even a galaxy that's 10 megaparsecs away, which is not very far by the standards of galaxies, it's still pretty local, I can't separate individual, certainly not low mass stars. I can separate out the brightest stars like Cepheids, which is why the Cepheid distance ladder works. But I certainly can't separate out stars like the sun or lower mass than the sun. There are just too many of them and they're too dim and they just all blur together. So you can't do star counting anymore, but you can still get a handle on the IMF from other techniques. And there are two main methods people use. One is spectra. There are certain spectral features that are produced only in a narrow range of stellar masses. And I have an example here. All right, so in this paper by Van Dokken and Conroy, if you look at the top panel, you'll see this sodium-1 band, Na1. There's this absorption feature that comes from sodium-1, and it's produced really only in dwarf M stars. And if you measure the depth of this feature relative to the background, you get a sense of how many M dwarf stars there are. Those are things that are about 0.1 to 0.2 solar masses versus more massive stars, things that are, say, 0.3 to 0.5 solar masses. So you can use the spectrum to get a handle on the IMF, and you can fit a model, and you can try and infer what the IMF looks like. That's one way. Another way you can go about it is you can use the mass to light ratio. You can measure the total amount of light, and that's sensitive to the IMF, because if you have more low mass stars, well, low mass stars are dimmer than high mass ones per unit mass. So if you have more low mass stars, you'll have a higher mass to light ratio. You'll get less light for the same amount of mass. So you measure the light with your telescope, and then you measure the mass of the stars producing that light with an independent method, like, for example, gravitational lensing, or using the dynamics by figuring, well, I see a galaxy, it has to be in dynamical equilibrium, the amount of gravity holding these stars together has to be, it tells me how much mass is there, and so you measure the mass to light ratio that way. So this gives you a way of measuring something about the IMF, not its full functional form, but something about it for more distant galaxies. And if you do that, you make the following interesting discovery. You find evidence for mild variation in the IMF. All right, so what I've plotted here is a paper from Gu et al. 2022. And the x-axis is the galactic velocity dispersion, which is basically a proxy for how massive or dense the galaxy is. On the left, at sigma of 200 kilometers a second or less, you have things that look like the Milky Way. And on the right, at 300 solar kilometers per second, you have massive early type galaxies, the sort of giant ellipticals you'd find at the center of a galaxy cluster. And what's on the y-axis is the mass to light ratio normalized to the one we infer for the solar neighborhood. And you can see there are very large error bars here. Any individual measurement is pretty poor, but there's a clear statistical signal that as you move to the right, the mass to light ratio is going up. Massive early type elliptical galaxies have higher mass to light ratios than lower mass ones. Now, it's a very weak effect. I want to emphasize this. We're changing the mass to light ratio by a factor of 2. This is not a big effect. So the IMF is still pretty damn universal. You go from the wimpiest star-forming galaxies in the universe, things like the Magellanic Clouds that are wimpier than the Milky Way, to the biggest galaxies in the universe, and the mass to light ratio of the stars changes by a factor of 2. Nonetheless, the fact that it's changing is a useful monoxide turns out to be one of the most abundant. And carbon monoxide emits radio waves that you can observe. And if you observe it across the sky, you see a picture that looks like this. So you have these clouds, which have a total mass, if you add up all of the ones in the galaxy, of order 10 to the 9 times the mass of the sun, so a billion solar masses. And these clouds are very dusty and they're opaque to starlight. You can't see through them. If you look towards one in optical light, you will only see blackness because the dust is absorbing all the light. So you can see them in radio, but in optical, they just look dark. Now, the behavior of these clouds as they collapse under gravity is interesting. And it's something that until you start working on the interstellar medium or interstellar gas clouds, it's hard to develop an intuition for. Now, a key point is that because these clouds are basically vacuumed by the standards of Earth, they don't behave anything like the air in this room. Just to give some emphasis. All right, now here I'm going to start talking about low density versus high density interstellar gas clouds. So low density might be a density of 1 to 100 atoms per cubic centimeter. High density would be 1 million atoms per cubic centimeter. The density of the air you are currently breathing is something like 10 to the 20 atoms per cubic centimeter. 10 to the 6 atoms per cubic centimeter is better than the best vacuum chamber we humans know how to make. So everything I'm talking about here is vacuum by the standards of Earth, but slightly different flavors of vacuum. Lower density versus higher density vacuum. And even though there are only, maybe 1 atom per cubic centimeter is the mean in the galaxy, there are a whole lot of cubic centimeters of space in the galaxy, which is how we wind up with 1 billion solar masses worth of atoms. All right, but because the density is very low, these gases do not behave like we're used to on Earth. So their temperatures are mainly controlled by radiative heating and cooling processes. The main heating processes are ionization by cosmic rays and radiative heating of dust by stars that are embedded within the gas. And then the warm dust heats up the gas it's mixed with by collisions. Cooling is via collisionally excited metal lines, which I'll explain more in a second, and radiation from that same dust that's mixed into the gas. The collisionally excited metal lines, what I mean are things like the scale emission that we're observing. If I have a cloud full of molecules of carbon monoxide and H2, Every so often, one of those H2 molecules will run into a carbon monoxide molecule, and it will become excited. That removes kinetic energy from the gas and puts it into the internal energy of the, say, carbon monoxide molecule that starts spinning. That carbon monoxide molecule can then emit a photon, and if that photon escapes from the cloud, the energy is lost, and so this is a cooling process. Kinetic energy goes down because it's radiated away. All right, so that's one fact about these clouds. Their temperatures are entirely controlled by radiation, not by any of the things that were used, like conduction, which are important on Earth. Even though the gas is mostly neutral, there is a very low density of free electrons coming from ionization from things like cosmic rays. And there are enough free electrons, it doesn't take very many, 1 in a million is more than enough, to carry a current, which means that this gas is going to be magnetized. There's current running through it. The time to achieve thermal balance is very fast, about 1,000 years, compared to, say, 1 million years for the gas to move anywhere, which means the gas is approximately isothermal. You can compress it, you can shock it, and heat it up. It will immediately return to its equilibrium temperature. The internal motions of this gas are much, much faster than the sound speed of the gas. And that's because the gas is able to cool so quickly it reaches low temperature. Right, which means that these clouds are described by supersonic magnetized near isothermal turbulence. Now, what does that look like? It looks like this. Here's a map of one of these clouds in detail. The color is just showing you different velocities. So when you make one of these maps in the radio, you can, by the Doppler effect, tell the velocity of the material you're looking at, and you see material with all sorts of velocities. So green, red, and blue are just 3 different velocity channels here, and you see this complicated structure. You can see this striated filamentary structure. That's coming from the magnetic fields. The gas is bound to magnetic field lines. As you can imagine, figuring out the dynamics of stuff like this is a messy process. So, however, being theorists, we are not daunted by messiness. We instead say, let's do some dimensional analysis. And as soon as we do that, we discover a problem. Isothermal turbulence is scale-free. So it can't possibly explain why the IMF has a favored mass. Now let me unpack that statement a little bit. Here are the basic equations describing an isothermal magnetized self-gravitating gas. I put them up here partly for intimidation value, but partly to make a point. The first one here just says mass is conserved. It says that the change in density at a given position, d rho dt, is simply the divergence of rho times velocity, just the rate at which mass flows in or out of that point. The second equation is conservation of momentum. It says the change of momentum density in given point is given by the flow rate, and then I have terms describing pressure forces, magnetic forces, and gravity. I have an equation that describes how the magnetic field changes. This is called the induction equation. And then I have the Poisson equation for self-gravity. Now, the thing about these equations is, being a theorist, the first thing I do is I non-dimensionalize them. I say, okay, let's just divide out the average velocity in this gas. Let's divide out the sound speed. Let's divide out the magnetic field and things like that. And let's rewrite this equation in dimensionless variables. All right, that's what I've done here. This is the exact same equation, except that now I've changed the density rho to r. I've changed the velocity v to u. And all of these things are now dimensionless numbers. And in so doing, I have discovered the important dimensions in the problem, or the important numbers in the problem. They all appear in the momentum equation. All right, you can see that they're all in the denominator on the right-hand side. We call these numbers the Mach number, m, the alphane Mach number, Na, and the virial ratio, alpha. And these have a very simple physical meaning. The Mach number tells me how important thermal pressure is. The alphane Mach number tells me how important magnetic forces are. And the virial parameter tells me how important gravity is. These 3 numbers dictate everything. Now, here's the problem. Here's what I mean by scale-free. Suppose that I were to just take my star-forming cloud and I were to wave a magic wand. And with my magic wand, I were just increase the density everywhere by some factor x. All all right, I am a god, I come and I cast my spell over the star-forming cloud, it gets denser everywhere. But that's not all I do. I'll also shrink it. I'll shrink it by x to the minus a half. All right, so if I make it 4 times denser everywhere, I'll make it twice as small, or twice as, I'll reduce its size by a factor of 2. And I'll also do the same to its magnetic field. I'll reduce its magnetic field by a factor of 2. Now, if I do that, all of these dimensionless numbers will remain completely unchanged. And what that tells me is that the evolution of my new magically ensorcelled cloud will be exactly the same as the one I started with, just scaled up or down, just a miniature version. On the other hand, the masses of whatever stars form in that cloud will not be the stars that have. So I cast my magic spell, the cloud, it behaves in exactly the same way, but now it makes stars that are a factor of 2 small in mass. That immediately tells us that these equations do not have enough physics in them to explain where the masses of stars come from. Now, if you don't believe me, you can believe a computer. You can do some simulations. So here are some simulations done by David Gusenyov, who is a collaborator of mine, showing the distribution of masses in a collapsing cloud. And all of these lines are showing mass distributions. The difference between them, the difference between the lines is simply the resolution of the simulation, how many particles were used in the simulation. And what I want you to notice is that the mass distribution is basically always just a power law in this plot. It's a straight line until you get to the minimum resolvable mass in the simulation, which is the point at which, well, I'm down to, there's only one particle. I can't have an object smaller than that. So what this is telling you is that these simulations produce not a distribution with a distinct peak, but a power law, not the characteristic mass of the IMF we observe. So how do we get around this? What does explain the peak of the IMF? Well, and the answer I will propose is that the gas isn't really isothermal, it's only mostly isothermal. All right, and the reason it's not really completely isothermal is that as the gas collapses, it will eventually form the seed of a star. All right, now it turns out, for reasons I can explain if you want, but for now, just trust me, when gas is collapsing to form a star, it first becomes hydrostatic and stops collapsing when it achieves a mass of about 1/100th the mass of the Sun, the mass of Jupiter, or a few times the mass of Jupiter. And at that point, I form a hydrostatic, non-collapsing object, and it's still growing. It's just the seed of the star. But all the mass that's now falling onto the seed hits the surface and stops. And all of its kinetic energy is then converted to heat. It gets very hot and is then radiated. And that radiation warms up the gas around the star. The result of this is an island of warm gas around each seed protostar. This matters because thermal pressure is the enemy of gravity. Thermal pressure wants to push stuff apart, prevent it from collapsing. Gravity wants to pull everything together. As long as the gas is cold, it will fragment into smaller and smaller bits, and that's exactly what that simulation is showing. But once it starts warming up, it can't do that anymore. Small bits of this gas now have too weak gravity compared to the thermal pressure to collapse. This is what halts that cascade of fragmentation. Now, the neat thing is, if you work through the size of the island of warm gas that's too warm to collapse, turns out to be dictated by the escape speed from the surface of the star, of the protostar, which at some level is not surprising, right? The higher the surface escape speed, the more kinetic energy in the stuff that's falling onto it when it shocks and stops, and therefore the more radiation I can put out. Higher surface escape speed, more efficient heater. The neat thing is that the surface escape speed from the center, from protostars, is dictated by something that is nearly universal, which is deuterium burning. Turns out when stars like the Sun form, before they're hot enough to burn hydrogen, for a brief period, they burn deuterium. You can burn deuterium at about a factor of 10 lower temperature than hydrogen. There isn't very much of it. This deuterium burning phase doesn't last very long simply because there's only one deuterium atom per 100,000 hydrogen atoms in the interstellar medium. But for a little while, you burn deuterium, and that deuterium burning, it turns out, sets the surface escape speed, which explains why the IMF is nearly universal. So again, you don't have to believe me, you can believe a computer. Here's a radiation hydrodynamic simulation of the formation of a star cluster. On the left side, you're seeing the gas density, and each of those dots is a star with its size proportional to its mass. And on the right, you're seeing the gas temperature. All right, that flickering you're seeing is real. It's basically because the rate of accretion onto these stars is varying up and down in time. And so the gas is sort of alternately heating up and cooling off. Nonetheless, you can see over time, there's a systematic increase in temperature. And you can measure what is the distribution of the masses of stars that comes out of this. So here's a plot of, since I want to plot this continually rather than showing you a histogram, I'm showing you the cumulative distribution. So the green line mostly stays inside the gray band. The reason the gray band is moving is that the total mass of stars is growing with time, and as the total mass of stars grows with time, the distribution changes. And the nice thing about a simulation, of course, is that we can always back up in time and understand what's going on in detail. So you can take this simulation and you can wind it back in time. You can identify for every star that forms the moment when it formed. And that's what we've done here. All right, so in this plot, each of these plots is just showing a snapshot of the gas in a region where a star is about to form. And we know the final masses of those stars. All right, I've labeled for each of these little circles what the final mass of the star that forms from this blob is. And here in this plot, I've selected, for the most part, ones that are near the average. Not all of them, the one to the bottom left is more massive, but nonetheless, you're looking at a bunch of stars that are near the average, and you can understand what sets their masses, what dictated how massive they became. You can do the following experiment. You can say, well, all right, let's, for each of these seed points where a star forms, let's just plot the profile of density and temperature and magnetic field around it. And let's measure how much gas can be supported against fragmentation by thermal pressure, magnetic pressure, etc. And let's compare that to how much mass is around these stars. So let's look at the bottom panel. X-axis here is distance from the star. And we're just looking at one of these examples, but the others look similar. All right, so X-axis is radius around the star. The black thick line is showing you how much mass is enclosed within that radius. Now let's just focus on the blue line. The blue line is showing you how much mass the thermal pressure can support. And what you see is that the thermal pressure can support more mass than the enclosed mass until you get out to about 1,000 astronomical units away from the star. And at that point, that dictates how much mass is available to collapse. And it turns out it's about 0.2 solar masses in this example, which explains why it went on to form about a 0.2 solar mass star. And you can repeat this for the other stars, and it's a pretty good predictor. Now, what about the variations in the IMF? I've told you about where the sort of universal peak comes from. What are the main channels of variation? Well, there are two of them. There's the fact that these galaxies that will receive variation have much higher ISM pressure and density. They also have different metallicity. If you go back to the early universe, the metallicity changes even more. Now, there are countervailing forces. Higher pressure and density favor fragmentation by making gravity stronger, more mass, more gravity, but they also trap stellar radiation more effectively, which heats the gas up and poses fragmentation. Fewer metals lead to less cooling, which reduces fragmentation, but they also mean less dust, so there's less trapping of stellar radiation and more fragmentation. So given these countervailing forces, you have to make a detailed calculation. And that's what Piyush and I did. So here are just temperature profiles of gas and dust around forming protostars for 3 different environments, one like the galaxy, one like a starburst galaxy, and one a primordial, very low metallicity environment. And you repeat this exercise of looking at the enclosed mass in solid lines and the mass that can be supported by thermal pressure in dashed lines. And you can find where these cross, and you discover the following interesting thing. The mass where those cross is at high pressure almost universal, but it does vary weakly with pressure. That is, if you go to higher pressure, which is what you have in these really dense star-forming galaxies, the characteristic mass is a little bit lower. It doesn't vary much with metallicity until you go back to the very early universe. If you go back to the very early universe, stars should have been much more massive. And we're currently checking these predictions with some simulations in a paper that will be on the archive within the week, hopefully. All right, so I think I have reached the end of my story. Here's my summary. The universe seems to favor stars with masses of about 2 times the solar mass. There's a little bit of variation around that, but not much. This requires a deviation from isothermal physics that mostly prevails in molecular clouds. And the most likely explanation is warm islands created when seed stars begin to heat up the gas around themselves. And the masses of these islands is determined by the star's surface escape speed, which is in turn set by nuclear physics, which explains the near universality of the peak mass. It's universal, but not completely. There's evidence for a more bottom-heavy IMF, more low-mass stars, in massive elliptical galaxies that are characterized by higher pressure than the Milky Way. And this can plausibly be explained as coming from the variations in gas heating and cooling associated with the different pressure that prevails in these galaxies. The effects are mild due to a near cancellation of opposing forces, but the residuals are enough that you can detect them. And if you go to the very early universe where the metallicities are much lower, you should get substantially more massive stars. And with that, I think I will end. Thank you for your attention. So I'm happy to take any questions that anyone has.
Yes, sir. Thank you so much. And we might have some questions from YouTube as well as from chat. So if Piyush could take it up, and then we can.
Everything I said makes perfect sense. No questions.
So maybe like I can begin, and like Piyush can collect the questions from YouTube and all. If that's not an issue. So,
Okay.
so yeah. So in that section of star forming clouds, so they collapse under their own gravity. So you said that you could explain if we are interested at some quantum mechanical ideas behind that.
I'm sorry. The sound is a little distorted. Can you say that? Can you say that
Yes,
again
sir.
and a little slowly, because it's not a great connection?
Yes, sir. So in the section of star forming clouds, so as the star they form by the collapse under their own gravity. So
Yes.
so in that you said that the inherent physics is quantum mechanical. So if you could like give us a little flavor of what it is.
Oh, so like why you can't see the H2? Is that the question?
Yes, sir. Yes, sir.
Yeah. So the basic reason is the simple harmonic oscillator. All right. So let me unpack that statement a little bit. All right. So you've probably taken a quantum mechanics course and you've learned about the quantum harmonic oscillator, right? The quantum version of the simple harmonic oscillator. And you've learned that just like the frequency of a spring, the natural frequency goes as the square root of the spring constant divided by the mass. All right, well, for a quantum harmonic oscillator, it's the same basic thing. The spacing of frequencies that are quantized, and therefore the spacing of energies, is proportional to 1 over the square root of the mass. Same is true for a quantum rotor. All right, so you can think of H2 as a little dumbbell, and its lowest excitation mode is not vibration, it's rotation. Same for CO. CO is a little asymmetric dumbbell. Its lowest excitation mode is rotation. The fundamental frequency spacing of that rotation goes as 1 over the square root of the mass. The mass of H2 is very low compared to the mass of CO. which means that the frequencies are very, very far apart. So the first excited state of H2 that is capable of radiating and giving you light turns out to be an energy above ground of about 500 Kelvin. Now, these clouds are just much, much colder than that. Their typical temperatures are more like 10 Kelvin. Now, what that means is there are simply no excited H2 molecules that are capable of radiating, because to excite them into that first state that's capable of radiating, it would require a collision with a kinetic energy comparable to 500 Kelvin, and that just doesn't happen in gas whose temperature is more like 10 Kelvin. On the other hand, the first excited state of CO that's capable of radiating is about 5 Kelvin above ground, and you have plenty of collisions that are capable of producing that. So that's the fundamental reason you can't see H2. It's that quantum mechanics dictates that its levels are very far apart, and they're so far apart that you just don't get any significant population of H2 molecules in the excited states capable of radiating throughout most of the volume of these clouds. You get a little bit of H2 radiation, but only in places where the gas has been shock heated up to an excessively high temperature of hundreds of Kelvin. And then you can get some H2 radiation, but those are the only places you get. That's the quantum mechanics.
Okay, sir. Thank you. So I think there's some questions in chats which we can take.
Yeah, one of the questions we got was, why do spherical galaxies have no heavy mass identification? This was asked by Varad.
So why are sort of elliptical galaxies more massive? Is that the basic question? Did I understand that correctly?
I guess.
Yeah. Well, so I mean, that's actually a really good and fundamental question in galaxy evolution. And I don't know that there's a completely satisfactory answer. We observe that there is a dichotomy of galaxies. Lower mass ones tend to be disky, have lots of gas in them, be star forming. More massive ones tend to be dominated by stars, have very little gas, and be more roundish. This probably has to do with the more massive ones having formed earlier in the universe when it was denser and having consumed their gas, and then perhaps having had a black hole blow out the remainder of their gas. But exactly why red galaxies look the way they do versus blue galaxies look the way they do is not a completely answered question. It's an active area of research in galaxy formation.
All right. Another question we got was, what process is theorized if it's not isothermal heat?
So what makes the gas not isothermal? I mean, the main thing is that stars heat it up. All right. So the key thing is that when you are forming a protostar and you're accreting onto it, all right, if I drop matter onto the sun, all right, suppose that I go out and I just take a kilogram of mass and I, use my rocket to get rid of its orbital velocity, then I just let it fall onto the sun. When it hits the surface of the sun, it's going really fast. When it hits the surface of the sun, it will shock and it will heat up to a temperature of millions of degrees, simply because all of that kinetic energy, which was originally gravitational potential energy, has been released, has been turned into heat when it slams into the surface of the sun and stops. That is a large energy source, and for protostars, that's the dominant energy source. While they're accreting, a star that's the mass of the sun, a protostar that's the mass of the sun, can be 10 or 100 times as bright as the sun, simply because of the energy being liberated by accretion. And that radiation goes somewhere. It is radiated away, and it then is absorbed by dust grains around the star, and those dust grains then collide with gas, or the gas collides with the dust, and that heats up the gas. That's what breaks the isothermality.
Thank you for your answer. And I guess that's all. Okay, there's another question.
Okay. this in the
If the
chat?
universe is really expanding outward, yeah, it's in the chat. If the universe is really expanding outwards, then why can we still see some stars in the same location since ancient time? Is it that a cosmic expansion holds true for only some regions of space?
Well, okay, so I mean, one thing I'd say is, well, what do you mean by in the same location? All right, so I'm not quite sure what's meant by that, but I can certainly just try and answer more generally. And so the universe is expanding, but that doesn't mean that like the molecules in my body are moving apart from one another, nor does it mean that the Milky Way, which is held together by its own gravity, is spreading apart. The Milky Way is not spreading apart. The Milky Way is held together by gravity. And so it is not the case that like the stars that you look up in the night sky and see with your naked eye are moving away from you. They are not. Anything you can see with your naked eye is part of the Milky Way, except for perhaps the Magellanic Clouds, which are also bound to it, to the Milky Way. And those are held in by gravity. They're not going anywhere. Expansion is happening in regions where things are not held together by gravity. Now, we can still see things that are beyond our own galaxy. And we can see them because the expansion of the universe hasn't put them outside of our horizon yet. All right, what I mean by that is that there's been enough time for light to get from them to us. If the expansion of the universe continues and continues accelerating, that horizon will gradually shrink. We will lose our ability to see really distant stuff. All right, but the only stuff that we're going to lose is the stuff that's not gravitationally held together to us. We'll still see the stars of the Milky Way. Those aren't going anywhere. It'll be the more distant galaxies that we're not gravitationally bound to that will disappear over the horizon if the expansion of the universe continues accelerating.
Was a star like Polaris, which was used by sailors in nighttime to know the location.
So it's not that that's moving away from us. The reason Polaris isn't in the same spot from our perspective anymore isn't Polaris moved, it's that the Earth moved. All right, so the Earth orbits around the sun with a tilt. So I don't know how well you can see this. If I stop sharing it, you can see my picture a little better. So here's the sun, here's the Earth orbiting around it, and here's the Earth's axis of rotation, which mostly maintains the same orientation over time. So as the Earth goes around the sun, the axis of rotation points in the same direction, and it points at Polaris. All right, but it is not the case that it stays pointing in the same direction forever. Because of interactions with, mostly with the moon, but also gravitational pulls from other things, the Earth's rotation, the Earth's axis of rotation actually undergoes nutation. It goes like this, it goes like a top. The time period over which that happens is about 10,000 years to complete a cycle. All right, so what that means is that, well, all right, now the north is pointing at Polaris, but if you go back a few thousand years, north was pointing a slightly different direction. So our North Star now is different than the North Star that people would have seen 2,000 years ago. If you go back 2,000 years before that, the North Star would have been different again. But that's not because the stars are doing anything. That's because the Earth's axis is changing its direction due to the gravitational influence, mostly of the moon. All right, so that's what's causing things to move. It's not that anything to do with the expansion of the universe or the stars moving. It's actually just the Earth turning and our perspective changing because
Okay, so I guess like I have a doubt that in the final part of the third section, you mentioned something like we basically derived that the mass is inversely proportional to the pressure.
it.
I
So
know that.
I said mass is related to the pressure.
Yes, sir. So like, why is this relationship there? Like, why is it that for high pressure the mass is low?
Right. So we have these sort of two countervailing effects. All right. One is that if I just pack, so all right, the way you can think about the fragmentation of gas is that it's a competition between two effects. It's a competition between gravity, which wants to drag everything together and wants to break stuff up into smaller and smaller pieces as they collapse, and pressure, which wants to smooth things out, right? Pressure wants things to be uniform. Now, I guess I realize saying it in terms of pressure is slightly confusing. If I cram more gas in, I am raising the pressure, but I'm also raising the density. And it turns out that's the more important effect. If the gas stays at the same temperature, yes, the pressure goes up, but there's more mass. And the effect of that extra mass making gravity stronger tends to break stuff up into more pieces. All right, so that's the fundamental reason that having a higher pressure galaxy with more mass in it tends to favor fragmenting into smaller pieces. Now, this is opposed by the fact that the temperature does not, in fact, remain constant. And that's because if I have more gas, there's more dust mixed with that gas, which traps starlight more effectively and warms the gas up, and that opposes fragmentation, that opposes breaking up into pieces. All right, but the fundamental reason that adding more mass favors fragmentation is it helps gravity win. If gravity wins, stuff breaks up and it collapses and it breaks up into infinitely small pieces if nothing ever opposes it. Hopefully that clarifies.
Yes, sir. Yes, sir. And like the final question, I think this will be that, like we said that the gas ceases to be isothermal at approximately 0.01 of mass of sun. So that why that factor of 0.01?
So where does that? Yes, I said that the gas stops collapsing.
Yes, sir.
When
Yes,
it reaches about 0.01 solar masses. The fundamental reason is that is the point at which it becomes opaque to its own cooling radiation. All right, so here's a way of thinking about gas that's collapsing. As it falls in, it needs to, in order to keep fragmenting, in order to keep collapsing, it needs to get rid of its gravitational potential energy, right? As it's falling in and getting denser, it's releasing gravitational potential energy. If that energy goes into heat and stays in heat, well, that will raise the pressure and that will halt the collapse. The heat will raise the pressure in the gas to the point where it can't keep falling. So in order to keep falling, in order to keep collapsing, it needs to radiate away that energy. But there's a limit to how fast you can radiate away energy. A fundamental limit is that because of the second law of thermodynamics, nothing radiates more efficiently than a black body. You can't, if you've got a certain size object, you can't shed heat faster than a black body of that same size and temperature. So there's a fundamental limit to how quickly you can get rid of your energy. So as this gas collapses, it runs into this fundamental limit where it can't get rid of its energy anymore. And it will halt collapse and form an object that is supported by thermal pressure. Now, there are several more complicated, because it turns out it's thermal pressure supported by H2 molecules, and once the temperature is high enough, those H2 molecules will dissociate, and you'll get what's called a second collapse, and that's what initiates the formation of the star. But fundamentally, where that mass is coming from is that's the point at which you can no longer shed your heat as quickly as you can collapse. And so you have to stop collapsing and wait to shed heat before you can collapse any further. You can continue collapsing, things can keep shrinking. They just can't do so in free fall because you can't radiate away your heat fast enough.
Thank you so much, sir.
Yeah, I guess that wraps up the questions part for today. That was all we received. We thank you again, Professor, for this amazing session, and we hope that everyone gained something new and learned something new today.
All right, well, thank you.